Good day. So I'm going to solve Physics 101 type of physics problem. It's an energy slash work problem. So let us read it first and then set out to deal with the questions it raises. A 2,100 kilogram pile driver is used to drive a steel I-beam into the ground. The pile driver falls 5 meters before coming into contact with the top of the beam, and it drives the beam 12.0 centimeters farther into the ground before coming to rest. Using energy considerations, calculate the average force the beam exerts on the pile driver while the pile driver is brought to rest. Okay, so actually, I think it helps to start this problem with a kind of drawing to see what is going on. So let me try to do that here. Let me thicken the line that I have. Let me erase this line now. So let me thicken. Hopefully this will be okay. So basically, the problem is something like this. So there's some object with which we are trying to make a hole in the ground. Okay. Actually, the book, it's from Serway and Jewett again, but the book didn't have a picture. But anyway, there's this object, and that's the I-beam. I don't know if that's what an I-beam really looks like, but it will suffice for explaining the problem. And then basically what happens is that this is the thing that we call the pile driver. Okay, so that's the pile driver. Sorry, driver. And that animal there is the I-beam. Okay, sorry, that didn't, okay. The font is not exactly Times New Roman. I apologize for that. But the story is the following. So the pile driver, so let's say MP is 2,100 kilograms. And it falls onto the I-beam. Okay, and I'm going to call this D 5.00 meters. Okay, and when it falls 5.00 meters, you know what? Actually, I have a better. This I'm going to call H. You will see why in a second. It's more communicative. So let me go back to pen. So I'm going to call this H, height. And I'm going to call the other distance, this one, depth. Okay. So basically, the pile driver falls onto the I-beam, and it falls 5 meters. Okay. And it drives the I-beam 12 centimeters farther into the ground before coming to rest. Okay. And we need energy considerations to calculate the average force the beam exerts on the pile driver while the pile driver is brought to rest. Okay, well, the point is that this object falls, okay? And first of all, before I go on, I'm going to say that I'm going to take the gravitational acceleration, just for simplicity, 10 meters per second squared. But I suggest that if you want more accurate results, you may want to do it with the more accurate number of 9.80 meters per second squared. Okay. Yeah. And the first thing that happens is as this object falls 5 meters, it loses potential energy and picks up kinetic energy. Okay, so the first idea that we use is energy. Sorry, that's not an R. Let me fix it. Energy conservation. Energy conservation. Okay, So the change in potential energy becomes kinetic energy. In other words, the kinetic energy of the object, so it starts out with kinetic energy 0, of course, before it's being dropped. It's dropped from rest, presumably. And the kinetic energy, when it reaches the I-beam, let me call that K, is mgh, right? M pile driver GH, which makes 2100 times 10 times 5.00 meters. Okay, and this is a 10 to all significant figures. Okay, so that's what I'm assuming. So that makes a very large number, right? So 21,000 times 5 is 105,000. And it's in joules. Okay, so that's the kinetic energy of the object. And I draw another picture. So now the pile driver has dropped. Here's the ground. Here's the I-beam. And the pile driver dropped onto the object here. Okay, but it's going fast. Okay, it picked up that much kinetic energy. Okay, and then, so now they both start to move. Okay, and eventually, we're going to go down to a depth D of 12 centimeters, 12.0 centimeters. Okay, yeah, 12.0 centimeters. And what happens is that this kinetic energy is going to be used up, so to speak, okay, as the pile driver drives the I-beam down 12 centimeters. And what actually happens is that work is being done, okay? Negative work, actually. No, sorry, wait, positive work. So the work being done is going to be the force times the displacement, okay? And when you don't know the spatial dependence of the force, so you know that the work normally is an integral of f dx, say, and you don't really know how the force varies here, okay? So that's why they're asking the average force, because here in an integral, let's say from x initial to x final, f in general is assumed to be it's assumed to be varying in space, okay? But we don't really know the spatial variation. But we can still say the following, that if I have a spatially varying force, xi to xf, fx dx, that's going to be equal to the average force times the total displacement. Okay, so this F bar is the average force. That's the average force. Okay, so, so what we can do is that we have the work, and what we want is the average force, and we have the displacement, which I indicated here, the depth to which the object goes, which is 0.12 meters. Okay, so from here, since we already calculated the work, we see that the average force is 105,000 divided by 0.12, and that's going to be, since this is in meters, this is in joules, it's going to be that many newtons. Okay, and I have to actually use my calculator to give you an exact number, which I will do shortly. Okay, so it's actually 105,000 divided by 0.12. That makes 875,000 Newton. Okay, so that's the average force in this case. 875,000 newtons. That would be our final answer.